Let us solve OpenStax University Physics, Volume 1, Chapter 4, Problem 40. A basketball is released 1.8 meters above the floor at 60 degrees. The center of the basket is 5.3 meters horizontally from the release point and 3.0 meters above the floor. Ignoring air resistance, what initial speed makes the ball pass through that target point? We need both coordinates of the same target event. A level ground range formula would erase the height difference. Translate the picture into coordinates before choosing equations. Put x equals 0 directly below the release point and put y equals 0 at the floor. The ball starts at 0, 1.8 meters. The target is the point 5.3 meters, 3.0 meters. The target is higher than the release point, but both y values are measured from the same floor reference. The unknown is the launch speed, v0. Enlarge the velocity triangle, rather than memorizing an unexplained component formula. The initial velocity is the hypotenuse. Use the familiar SOH-CA-TOA mnemonic. Ka says cosine equals adjacent over hypotenuse. So, cosine 60 degrees equals v0 x divided by v0. Solving for the adjacent side gives v0 x equals v0 cosine 60 degrees. SOH says sine equals opposite over hypotenuse. So sine 60 degrees equals v0 y divided by v0. Solving gives v0 y equals v0 sine 60 degrees. The triangle, together with SOH-CA-TOA, tells us both formulas. Now connect those component formulas to the kinematics equations. For constant acceleration, x equals x0 plus v0 x times t plus 1/2 times ax times t squared, and y equals y0 plus v0 y times t plus 1/2 times ay times t squared. Our coordinate choice makes x0 0. With no air resistance, ax is 0, while ay is negative g. The initial height is 1.8 meters. Finally, substitute the components from the velocity triangle. v0 x is v0 cosine 60 degrees, and v0 y is v0 sine 60 degrees. Therefore, x equals v0 cosine 60 degrees times t, and y equals 1.8 meters plus v0 sine 60 degrees times t minus 1/2 gt squared. Every term now comes from either general kinematics, the coordinate choice, or the velocity triangle. At the target event, call the shared time t1. Then x is the horizontal target distance, 5.3 meters, and y is the basket height, 3.0 meters. Substitute that same t1 into both motion equations. Horizontally, 5.3 equals v0 times cosine 60 degrees times t1. Vertically, 3.0 equals the initial height, 1.8, plus v0 times sine 60 degrees times t1, minus 1/2 g times t1 squared. Thus 5.3 and 3.0 come from the target coordinates, 1.8 comes from the release height, sine and cosine come from the velocity triangle, and the gravity term comes from ay equals negative g. The two unknowns are v0 and t1. Two independent component equations mean the setup is complete. Eliminate time systematically. Solve the simpler horizontal equation for t1, d divided by v0 cosine theta. Substitute that expression everywhere t1 appears in the vertical equation. Look closely at the term that was linear in time. v0 sine theta times d over v0 cosine theta. We are fortunate because the v0 factors cancel, leaving d tangent theta. That cancellation removes a possible first power dependence on v0. So here we only need to isolate v0 squared. In a related problem, where comparable terms do not cancel, the remaining equation may be quadratic in the chosen unknown, and the quadratic formula would be the general next step. The squared time term contains d squared over v0 squared times the cosine squared of theta. Now rearrange and isolate v0 squared. The boxed expression follows. This result was derived for this target geometry. Students do not need to memorize it as a new formula. Now, substitute d equals 5.3 meters, y0 equals 1.8 meters, h equals 3.0 meters, and theta equals 60 degrees. The calculation gives v0 squared equal to about 69.0 square meters per square second. Keep the positive square root, because v0 is a speed. The required launch speed is 8.31 meters per second. Check the result in the original component equations. The horizontal equation gives a target time of about 1.28 seconds. Substituting that time and the launch speed into the vertical equation returns 3 meters to the shown precision. Thus, the computed path reaches the stated point 5.3 meters, 3.0 meters, within our simplified projectile model. This is a consistency check on the algebra used in that model, not a claim that the model captures every basketball detail. In particular, the exercise treats the basket center as a point target and does not test whether the ball enters the rim at a usable angle. The reusable projectile targeting strategy is to translate the picture into start and target coordinates, resolve the launch vector from its triangle, and write horizontal and vertical equations for the same target time. Eliminate that shared time before inserting numbers, then check the result in both component equations. This approach works when the target is above, below, or level with the launch point.